Hey everyone, I'm Ollie. I'm from a company called Converge. So we're a young startup company about 3 years old, focusing on optimizing the construction industry. So some similar themes are going to cover as my previous topics, and I'm afraid I probably am also going to sound like a horse racing commentator because I'm going to try and fly through these slides. Just quickly, I'm going to try and cover some of the technical detail at the start, just so I'm not overloading you with information none of you comprehend. It's all pretty simple really, and if anyone wants some more in-depth discussion around it, please feel free to approach me afterwards, or we can come and do a CPD at your offices if that suits. So we're dealing primarily at the moment with the determination of strength of concrete. So this is compressive strength of concrete. Wherever concrete's on the critical pathway of a construction job, that's obviously going to be one of the primary causes of delays. And we see this quite a lot, some of the metrics that we've been through already with the industry being behind on growth and always delivering under budget, over budget. So there are some sort of consistent issues we're seeing come through here. A lot of this can relate to delays as a result of concrete strength. So some of you may or may not be familiar with how we can determine concrete strength usually. So we'll take samples of the concrete as it arrives to site. We'll usually take cube or cylinder samples. They're removed from the site, cured in fixed conditions, so 20 degrees centigrade, and then crushed at predetermined intervals. So there's several issues with that as a general approach. We've got a limited number of samples that are taken as the concrete arrives. They're being stored in entirely different conditions to the structure itself. It's quite time consuming just to convey this information back and forwards between a lab. And then lastly, it's very, very common that we get poor results come back, which generally speaking isn't a product of poor quality concrete, but is generally speaking just a product of a poorly prepared sample that gives a low result. And these often lead to quite lengthy investigations. Often we have to go and take core samples from the structure itself. So these are really lengthy and actually cost a lot of time and money in the process. So I'm not here to beat up on the traditional way of doing things. We've got an alternative methodology to achieve a similar end. So we use something called the maturity method. So this is a technique that dates back around 70 years. It's effectively based on the principle that concrete strength development is driven by a chemical reaction known as hydration. So this is an exothermic reaction, and as with any chemical reaction, so it's going to go faster in the warmer environments, and it'll slow down as it gets cooler. So it's all revolving around that principle. And it's a member of a class of techniques known as non-destructive techniques. So we don't actually, traditionally with concrete, you have to destroy the sample in itself to know what strength that is. But with these techniques, you needn't do that. You can determine the strength in other ways. So I'm going to paint a very, very quick example for you here and then move on to some slightly more fun stuff. So we see here, in effect, they would integrate underneath the temperature profile of the concrete itself. So that involves putting a temperature sensor into the concrete or curing it in a known temperature environment. And in the example you'll see on the left-hand side, we've cured a sample of concrete for 15 hours at 20 degrees. And when we integrate that, we get 300 degrees centigrade hours. And then in the example on the right, we're going to cure it for a shorter period of time at a warmer temperature. So in this case, 30 degrees in 10 hours. And as you'll notice, we get the same value of maturity out. And what the maturity method therefore states is, if these two samples made of the same mix design have the same maturity, then they should theoretically share the same value of strength. So we combine this with a calibration for the specific mix. So we effectively take lots of samples of the concrete and crush them. That allows us to determine this specific relationship between the maturity of concrete and its strength. And we can always refer back to this. So what this facilitates then is for us to effectively just place a temperature sensor into concrete, and that'll allow us to determine its compressive strength as an alternative to taking cubes and crushing those. The math can get a little bit more complicated, and I'm not going to bother explaining any more than that to you now. But again, feel free to come and ask me about it, or if you wanted us to do a CPD seminar, then we'd be glad to. So what does this mean for us? In effect, what we find is that concrete actually cures in drastically different environments. Again, this is where it's on the critical pathway. What we see quite frequently is concrete being used in high-rise structures, in the slabs, in the cores. And if the concrete is curing slower and therefore developing strength slower, it's going to slow down the overall delivery of the project and hence have late delivery on a project. So I'm just going to show you very quickly, and again we're looking at temperature here, and from this we can infer the strength. So you'll see two curves appear on the screen, one of which represents a cube being taken, and then one of which represents a slab, for example, and the temperature of both. So you'll see when we cast a thick element of concrete, then we get a higher temperature rise. It has more thermal mass and therefore generates more heat and retains more of that heat. Whereas the cube is a very small 100 mil by 100 mil cube. It's just going to lose a load of that heat straight off the bat. So when we perform a nice math, which I've just explained to you all and you'll all understand perfectly, we can integrate underneath these curves, determine their maturity, and from that we can calculate their value of strength. So as you see, the in situ concrete itself is around 30 newtons per millimeter squared, or megapascals, whereas our cube is actually a lot weaker. It's at 21.5 newtons per millimeter squared. So this is going to vary depending on the thickness of the element. We certainly see some instances where concrete in a cube is around half as strong, around a third as strong as the concrete within our structures themselves. And this is commonplace. This is going on every day around us. Every building you see being constructed, we're taking samples, curing them in a separate environment, and then inferring what strength we believe the structure itself should be. And this is just an example of a technique that can give us a means of determining the actual in situ strength. So in summary, very, very quickly, we perform a calibration, which is a one-off process, and then we can place sensors into the concrete to monitor the strength of those. So in terms of our setup in itself, we use a mesh network, what's known as a mesh network. So we install effectively a wireless network, quite similar to your home router setup, around the site in itself, and it has to be dynamic in case things move on construction sites. You get big sheets of steel getting put in the way. So the network itself is quite adaptive, and that allows us to monitor several locations at any given point in time. And we've used this technology in whole heaps of applications. So it can be used anywhere we're using ready-mix concrete effectively, so fresh, wet concrete coming onto site. The technique is applicable. Bread and butter, largely speaking, is high-rise construction, so we're dealing with the construction of frames effectively. We do a little bit in the ground, foundations, piling we're just starting to move into, and on the civil engineering side we're starting to do a little bit there too. We're hoping that we can deploy onto some fairly substantial sites soon, but there are other examples you see on the bottom right here. We've been helping TfL with some of their trap maintenance works, which happens overnights and on bank holiday weekends when the tube network shuts down. I'm not going to run through any of these, but if you recognise any of them, that's great. Some of the companies we've been working with over the last few years. So what can we do with this data? So we're collecting masses and masses of in situ concrete performance data. So effectively we're looking at different sites, different contractors, the different mixed designs, how they perform in situ, different concrete suppliers, different geographies. So we're building ultimately quite a substantial data set. And some of the smart stuff moving forwards that we're going to be able to do is to leverage that data to sort of use the big data analytics approach and start to generate some useful insights from that data. So just very quickly, a very straightforward example of this is we can run through our database, we can calculate the actual curing temperature of concrete at any given time of year. So again, we cure our samples of concrete in standard conditions. So all year round, whether it's the depths of winter or the middle of summer, we're going to cure the concrete in itself at 20 degrees centigrade, plus or minus 2. What you see here is based on a data set built up again of nearly 100 projects over several years. You see that concrete actually varies anywhere in curing temperature from sort of 12 degrees down in January up to sort of 33. And this is an average temperature of it. It'll actually get much higher in terms of its peak temperature. But what we can do using some of the science we covered earlier is to infer how fast this is curing versus our cubes. So just again quickly to highlight that, all year round our cubes in standard conditions are just going to cure at a fixed temperature. But using this we can now infer exactly how fast the concrete cures. So we know in the depths of winter that concrete is actually curing a third slower than those cubes are going to give us credit for a few months of the year. And all the way through to the depths of summer where we can actually find our concrete's curing twice as quickly. So this is some of the value we deliver to customers, is just giving them a real feel for in situ performance. So instead of just relying on cube data procured in standard conditions, they can actually start to leverage some of this. It's all available on a web platform, as you may have seen with the others, which is available on any mobile device. It leverages some of those benefits of web applications. So then how are we going to use that data moving forward? So some of this is functionality that is present already, and some of this is stuff that we're building in. And I've tried to lay it out in pre-project, mid-project, post-project to give you a flavour of where this is going to start to influence the project lifecycle overall. So currently we tend to operate within the mid-project zone at the moment, which is helping people build things today. But as we move forwards, again, and the data set grows and we can start to infer more useful stuff out of that, we can actually look at both program optimization, mixed design optimization. So as they're going into their project, we can say, you know, what geography is this in? What supplies are available to you in your local, you know, within a reasonable radius? We can determine based on what mixed design constituents they have available, exactly what mix that should look like. How is that going to influence the program? Have you made realistic or unrealistic assumptions on what's possible based on concrete performance? You know, you'd be amazed to see how many people design a program and don't actually take account of any variability from summer to winter, which just isn't realistic, being frank. And again, I could show you the slide. But you can see here just how significant this variability in performance can be. And what we're just showing there is the time to reach certain strength milestones. In terms of mid-project, so again, today we can tell someone what the strength of their concrete as of right now, but what we're building into the platform using machine learning algorithms is effectively, and again, crunching that big data set, is the ability to sort of forecast. So I can know what my concrete, you know, I can know how strong the concrete is on floor 37 of the tower I'm constructing right now. But as I leave the site for the evening, I'd be really interested to know, you know, when is it going to reach the strength I require? Exactly when's that going to happen? How can I get my guys into place? So some of the functionality we're building in revolves around forecasting that performance based on data we've seen in the past, based on the data we're seeing on that site up until that time. And then we can effectively just run our forecast, determine how long we think it's going to take to reach their required strengths. And that will then help them get their guys into position in a prompt manner the next day. Or, you know, be it a week later or however long that takes. Then moving into post-project. So as we come to the conclusion of projects, the hope is that we can now start to visualize and model some of this data. Again, we're looking at the time it's taken to reach a certain strength. So in this case, this is a project where they're doing post-tension slabs. They perform an initial tension at 10 newtons and a final tension at 25. And you can see here the time it took to reach that strength milestone. So in summer, we're down at 2 days. In the depths of winter, that's up at 10 days. And just to reiterate, all through the year, they're seeing exactly the same flat performance with no real impression of how that concrete is performing through the year. So using this data, then they can start to infer, you know, perhaps I should be leaving a few days, you know, extra in December through January to account for that slowdown. But actually, as I get into the summer, perhaps I can leverage some of that those gains and actually start to build this into my program and rely on faster strike times or tensioning at a faster rate. And then the ultimate hope is that as we get to this point, some of these insights are going to feed back into the pre-construction phase, that they'll be able to take these insights we're generating, feed that into the programming at the outset of the project, and then that will facilitate having a nice, well-optimized program throughout the whole project's life cycle. So I think that will probably wrap up my 10 minutes. Thank you very much all for your time, and look forward to any questions.